Okay, so in this first example, we are being asked to. So example number 1 in figure 1, the tension in the horizontal chord is 30 newtons. Find the weight of the object. So we have got 3 ropes. There's this rope here, chord 1. There's another one here, rope number 2, chord 2. And there's a third one, which is what we have been given here. Then the first rope is the one which is supporting this weight which we are supposed to find. Is that clear to everyone? Now, for us to find the weight of this particular object, which is being shown as FW here, we need to know how much tension is in each of these ropes. For this particular...
Sir, is the class being recorded?
Yes. For this particular rope, which we have here, which is the horizontal rope in this particular direction, the tension in this rope is 30 newtons and the direction of the tension is as shown here. So the tension in this particular direction here. The other one, for this particular rope, the tension is that way, and for this other one, the tension is up like this, and hence supporting this thing here. Now, for this thing to be the way it is, basically what's happening is that this point which you have here, the point P, has to remain motionless. And when the point P remains motionless, it basically means that there will be no acceleration. And at the same time, the amount of tension which is going to be in this rope will be the same as the weight of this particular object. So by us finding how much tension is in this rope, we will actually be finding also the weight of this object. So the thing which we do, if we are to make sure that this particular point P here remains motionless and does not move, what you're going to do is, if you have your notes printed out, you sketch about this point. You draw with a pencil in this direction. So this is going to be your x-axis. So your x-axis is going to be in this direction. Then your y-axis will be in this direction. So you draw an xy plane about this point P. Are we clear? Is it clear? You draw an xy plane. So this is going to be your x-axis in this direction. Then this is going to be your y-axis. So basically you draw an xy plane about this point P. Is it clear?
Yes, sir.
So once you draw your xy plane about this point, if this is your yesterday I asked people to print out these notes. So I'm hoping people have done that. So you use a pencil, so you draw a straight line, a horizontal line along this, which is going to pass through this rope. So that's going to be your x-axis. Then you also draw a vertical line which is going to pass through this point. That's going to be your y-axis. So we are going to choose this side to be our positive x-axis. If we choose this side to be our positive x-axis, then this other side is going to be our negative x-axis. If we choose up here, the y-axis up here, we choose that to be our positive y-axis. Then down here in this particular direction, that's going to be our negative y-axis. So if you choose this side to be a positive x-axis, then this side is going to be negative x-axis. If on the other hand, if you choose this side to be a positive x-axis, then this side is going to be a negative x-axis. So in our case, we just decide to choose this side to be our positive x-axis. So when we choose this side to be our positive x-axis, the other thing we need to be aware of is the fact that these tensions which are in these ropes, these are vectors. Tension is a force and force is a vector. So when we're talking about a vector, we need to concern ourselves with the angle with which this particular vector makes with the positive x-axis, because we measure our angles from the positive x-axis. So for this particular rope, which lies along our what we have chosen to be our positive x-axis, the angle which this particular tension makes is going to be 0. In the case of this rope here, if we are measuring from this side, the angle which is going to make all the way up to there, from here all the way up to there, is going to be 90 degrees plus 50 degrees, and that's going to be 140 degrees. In the case of this rope which we have here, the angle which this rope makes with this positive x-axis will be something which you're going to measure like that, all the way up to there. So you should show with a pencil all the way up to there. That's going to be the angle which this rope is going to make, and that angle turns out to be 270 degrees. Are we clear? So you need to draw you need to draw an xy plane over this point P. You draw an xy plane over this point P. Then you choose either this side or the other side to be your positive x-axis. If we choose this side to be our positive x-axis, then this rope makes an angle of 0 degrees. This other rope here makes an angle of 140 degrees. Then this rope will make an angle of 270 degrees. Since this rope has been named code 1, we are going to call the tension in this rope FT1. And since this rope has been named code 2, we're going to call the tension which lives in this rope FT2. And since this rope is just given 30 degrees, we are going to call the tension which is in this rope to be 30 degrees. So the steps, like I said before, is when you're trying to work out a problem to do with equilibrium, you need to identify which point has to remain motionless. You need to isolate, and what we have isolated is this point P, to say this point P needs to remain motionless. Then after that, you identify which forces are acting on this particular point. In that case, we have got a force which lives in this rope, which we know is 30 newtons. There is another force, a tension, which lives in this rope. We still don't know what it is yet. We need to find it. Then there's another one which lives in this rope. The tension which lives in this rope is equal to the weight of this particular object. And once we find this tension, then we'll be able to find the weight of this particular object. So once you identify which forces are acting on your point of interest, you need to find the components of these particular forces. You need to find the x component, you need to find the y components of these particular forces. So when you do that, that's where you are going to create a table which looks like this. You're going to create a table of components which looks like this, where you're going to have a vector this side, you're going to have your x component this side, you're going to have your y component this side. So for the force which lives in code 1, we're going to call that tension 1. So for this particular tension, the x component of this tension, whatever it is, we're going to call it T1. So because it lives in the first rope, so we're going to call it T1. Then the x component of this force will be T1 cos 270 degrees. The angle it makes, the angle that particular rope 1, code 1 makes with what we have chosen to be our x-axis, this chord with what we've chosen to be our x-axis is 270 degrees from there all the way up to here. So the angle that which that chord makes is 270 degrees. So we're going to end up with T1 cos 270 degrees. That's going to give you 0 newtons. For the y component, you're going to have T1 sine 270 degrees, and you're going to end up with minus t. For the other, so the x component of the tension in the first chord is going to be 0, and the y component is just going to be minus t. Then for the other bit, the chord which is in the second rope, the tension which is in the second rope, this one. So we're calling the tension in this rope T2. Okay, so that's going to be T2. Then the angle it makes from this positive x-axis up to there is 114. So we're going to have the tension being equals to So the tension is T2. The x component of this tension is going to be T2 cos 140 degrees. That's going to give us minus 0.77 T2. Then the y component is going to be T2 sin 140 degrees. We're going to end up with 0.64 T2. Are we clear? Are we clear?
Yes, sir.
Next, we move to T3. So T3 is the tension which is going to be in this rope. So we're going to call this rope, since this one is code 1, this one is code 2, we can call this one code 3. So the tension in this rope is going to be T3. And we know how much T3 is. T3, we've got a size that is 30 newtons. So the x component of this T3 and the angle which this chord makes with the x-axis, since we have chosen to draw an xy plane over this particular thing, running over this point. So the angle is 0 degrees. So we're going to end up with T3. We're going to end up with T3, which is 30 newtons cos 0 degrees, and that's going to give you 30 newtons. And the other side, for the x component, and for the y component, you're going to have 30 newtons sine 0 degrees. You're going to end up with 0 newtons. So this is the first thing which you're supposed to do. So the steps are as follows. 1, you identify the part, or you identify which part of this diagram needs to remain motionless. Once you identify the part of the diagram which needs to remain motionless, the next thing you're going to do, you identify which forces are acting on this particular part of the diagram. Then after that, on this particular point you have chosen, say this is the thing which is not supposed to move, you draw an xy plane over that, clearly showing which one is the positive x-axis, which one is the negative x-axis, positive y-axis, negative y-axis. Then once you do that, then you start working out the components using a table like this. Okay. Once you have worked out the components, the next thing you need to do is you need to add the x components, or the components on the table. So we add 0 newtons plus minus 0.77 T2 plus 30 newtons. When you add all these things, they should give us 0. We should force them to become 0. Then we also do the same thing inside. T1 plus this much thing plus that, we should get 0. So that's the next thing which you need to do. So when you do that, when we add all the forces along the x-axis, so the sum of the forces along the x-axis, which is because the sum of the along the x-axis, so the sum of the x components of the forces, that's going to be 0 newtons plus minus 0.77 T2 plus 30 newtons equals to 0. So when this bit goes the other side, you're going to end up with 0.77 T2 equals to 30 newtons. Then you're going to end up with T2 equals to 30 newtons divided by 0.77. You're going to end up with 39 newtons as the force, as the tension which is living in the second rope. Are we clear? Once you have your components in a table, your x components and y, you simply add them, and you make sure when you add them, they should add up to 0, because that's the only way you're going to have equilibrium. You only have equilibrium when you force things to be equal to 0. Okay, so we find our T2 to be equal to 39. Next bit is we are going to add the y components, these components, the T1 plus this plus that. So when you add them up, when you add up the y components, the sum of the force along the y-axis, that's going to be 0. So you're going to have this, the sum of the forces, that's going to be minus T1 plus 0.64 T2 plus 0 newtons equals to 0. So when you do that, we're going to end up with, so this bit, we take to the other side, you're going to end up with T1 equals to 0.64 T2. But we have already found out what T2 is. Our T2 we have found to be equals to 39 newtons. So in that particular case, when we make our substitution of these things, so we're going to end up with T1 equals to 0.64 times 39 newtons equals to 25 newtons. Are we clear? So we have found how much tension is in the first drop. Now, because this thing remains the same, it remains motionless. The object we're interested in, this particular object remains the same. It remains motionless here. When you have an object hanging, being supported by a rope, and that particular object does not move, it simply means that the weight of that particular object is equal to the tension which is that rope. So the rope can produce different values of tension depending on how much weight is hanging on it. So the tension in this rope, which you have found to be 25, is the same as the weight of the object which we have hanging there. So we conclude that. So we make the following conclusion, that the weight of the object is equal to the tension in the first rope, and we end up having the weight of the object being equals to 25 newtons. Is that clear? Is it clear? Okay.
Yes, sir.
So, with that bit, any questions? Are there any questions? We need to move on to another example. Example number 2. Now, in example number 2, as shown in figure 2, a 50 Newton box is slid straight across the floor at constant speed by a force of 25 newtons. So the question being asked is, how large is the friction force which impedes the motion of the box? Then B, what's the other thing? What's the other question? How large is the normal force? Then C, what are we being asked again? Or C, find the coefficient of kinetic friction between the box and the floor. Now what we have here is this box. This is the box where they're talking about. And this box is sliding across this floor. Now, as this box is sliding across this floor, it's sliding at constant velocity. Are we clear? The box is sliding at constant velocity. Now, if the box is sliding at constant velocity, what that simply means is that there is no acceleration. So the box is in equilibrium. Now, the kind of equilibrium which an object has when it's moving with constant velocity, that is what is called kinetic equilibrium. The equilibrium in the problem we just looked at here, the problem where this point P was not moving, this point, if something remains motionless, this kind of equilibrium, that's what's called static equilibrium. The other kind of equilibrium where you have an object moving with constant velocity, that kind of equilibrium is what is called kinetic equilibrium. So, the object which is supposed to be in equilibrium is the box. Are we clear? Is it clear? The object which is supposed to be in equilibrium is the box. So you need to identify which object is supposed to be in equilibrium. So in this particular case, the object which is supposed to be in equilibrium is the box. Once we identify which object is supposed to be in equilibrium, the next step you have to do is you have to identify what kind of forces are acting on this particular object. What kind of forces are acting on this particular object? For as you can see in this particular diagram which we have, this box has got mass. If a box has got mass or anything else has got mass, it means that this particular box has got weight. And the weight is going to act downwards. So the weight of this particular box, which is sliding across this floor, is going to be pointed downwards and it will be acting against the floor. Now the floor is going to feel this weight and the floor will not be happy about this. So the floor will push back against the box through this force Fn. So the weight of the box is pointing downwards. It always acts downwards. For a flat floor like this one, the floor will not be happy and the floor is going to push against the box upwards through this force here, Fn. At the same time, since this box is moving in this direction, The reason why the box is moving in this direction is because it's being pulled by a rope there, acting in that direction. So if it's being pulled by a rope in that direction, it means that there's a tension which is acting in that direction, and the size of that tension is 25 newtons. It makes an angle of 40 degrees to the horizontal like this. So it's not the whole 25 newtons which is pulling the rope, the box this side. Since the box is moving in this direction, there has to be friction to oppose the motion of the box, and the friction is pointing in this particular direction. So this is the next step which you have to do. After you identify what object has to be in equilibrium, you need to identify which forces are acting on this particular object. Now, all these forces acting on this object are vectors. What we mean when we say vectors, it means that these forces have got size and these forces have got direction. They have got size and direction. So if a quantity has got size and direction, it's a vector. It simply means that you can move it around as long as you do not change the size of that particular force, you do not change the direction of that particular object. So with this realization that these things are vectors, it simply means that we can move them around. But the question is, you're going to move them around to where? Where do you want to move them to? When you realize that, oh, these things are vectors, therefore I can move them around. Where do you want to move them to? You want to move them to an XY plane. So the next thing you need to do is, at the center of this box, you draw an XY plane along this direction. So if you've got your node somewhere, so you draw a parallel line like this. So along this direction, this is going to be your x-axis. Then up like this, that's going to be your y-axis. So in this direction, like this, that's going to be your, straight with this line. Like that, that's going to be your x-axis. Then up at 90 degrees, that's going to be a y-axis. That's the next thing you're supposed to do. If you've got something like a box like this, something which is not small, so you just go to the center, then, because why do you go to the center? Because the mass or the weight of this particular object is concentrated at the center. So you draw at the center, you sketch, you put your XY plane there. Now, when you put your XY plane there, the next thing you're supposed to do is, this problem is different from what we had. The first question you looked at. In the first question, nothing was moving. In this particular problem, something is moving. So the direction in which this box is going to be moving is going to be moving in this direction. So you choose the direction in which the box is moving to be your positive x-axis. So I hope by now people have sketched an XY plane over this box. Then since this box is being pulled in this direction, you choose this side of the XY of the x-axis. You choose this side of the x-axis to be your positive x-axis. Are we clear?
Yes, sir.
Then you get this force. This one you can leave it. It's already pointing down. But you can get this one. You lift it, you put it up so that it's pointing along the y-axis upwards. It's a vector, so you can lift it as long as the size of the force is the same. You lift it, you point it up, because it's already pointing up. So you just lift it from here, lift it, then you sketch, say the normal force is pointing up like this. This other one here, this one is 25 newtons, makes an angle of 40 degrees. You can lift it, you can put it here so that it points in this direction here, like that. So that it makes an angle of 45 or 40 degrees. You have a 40, you lift the way it is, you come and put it here. When you're lifting your vectors, you're not changing anything, because the size of the vector and the direction are still the same. So the vector hasn't changed in any way. You get this guy here, you lift it, you come and put it here so that it points in this direction. All these forces, you want to make sure that they are starting from the origin of your XY plane. Are we clear?
Yes.
Once you do that, you have your forces, you've got your XY plane. This side is a positive x-axis. Positive x-axis because that's the direction in which the box is moving. The opposite is the negative x-axis. Then up in this direction is the positive y-axis. Down below is the negative y-axis. So you'll be measuring your angles from the positive x-axis. So when you do that, this particular force, this 25 newtons, makes an angle of 40 degrees. This one, which is going to be pointing up like this, is going to make an angle of 90 degrees with a positive x-axis. This other guy here is going to make an angle of 180 degrees. This weight, which is pointing down here, is going to be making an angle of 270 degrees. Is that clear?
Yes, sir.
So with that information, then you can proceed to work out what are the x components and the y components of each of these vectors. What is the x component and y components of the 25? What is the x and y component of the normal force, which will be pointing up this way? What is the x and y component of the friction force, which will be pointing in this direction? What is the x and y component of the weight, which is going to be pointing in this particular direction? When you do that, so you need to do that in a table. The table which you're going to use for that particular purpose needs to look like this. So for the tension in the rope, that's what you're calling Ft, or we could have just called it T. For the tension in the rope, Ft, so that's going to be the tension in the rope, which is 25 newtons, cos 40 degrees. So that's going to be 25 times cos 40 degrees. So you're going to have your x component of the tension as 19.2. The y component of the tension is going to be Ft sine 40 degrees. So you're going to have 25 newtons times 40 degrees. So you're going to have 16.1. When it comes to the friction force makes an angle of 180 degrees with a positive x-axis. So you're going to have whatever the friction force is multiplied by cos 180 degrees. You're going to end up with minus Ff. Then for the y component, you're going to have the friction force multiplied by sine 180 degrees. You're going to end up with 0 newtons. Then for the normal force will be pointing up. So you're going to have the normal force multiplied by cos 90 degrees. That's going to give you a 0. Then for the y component, you're going to have the normal force multiplied by sine 90 degrees. You're going to end up with Fn. For the weight of this particular box, you're going to have the weight of the box multiplied by cos 270 degrees. You're going to end up with 0 for the x component. And for the y component, you're going to have the weight of the box multiplied by sine 270 degrees, and you're going to end up with minus Fw. Is it clear?
Yes, sir.
So once you have your components in a table like this, then you simply add them. You add your components, you add your x components, and you make sure that they should add up to 0. So you add your x components and you make sure that they should add up to 0. So when you do that, so in our case, our x components are, we have this one here, 19.2 newtons plus minus friction force plus 0 plus 0. This should give us 0, should add up to 0. So when you do that, for the x components, you're going to have the sum of the forces along the x direction. They should add up to 0. So you're going to have 19.2 newtons plus minus the friction force plus 0 plus 0. That should give you 0. So you're going to end up with 19.2 newtons minus the friction force equals to 0. So then you get this guy to the other side. You're going to end up with the friction force being equals to 19.2 newtons. Are we clear? So you find the friction force to be 19.2 newtons. Is it clear?
Yes, it is.
Next, you add your y components. You have got 16.1 plus 0 plus this guy plus the weight of the box. And the weight of the box we've been given. The weight of the box is 50 newtons. So we add everything up. So when you do that, so we add everything along the y, so that we're going to have, so the sum of all the components along the y, they should give us equals to 0. So you're going to have 16.1 newtons plus 0 newtons plus minus Fw plus Fn equals to 0. So our weight is 50, so you're going to have 16.1 newtons plus 0 newtons minus 50 newtons plus Fn equals to 0. So you're going to have 16.1 plus 0 minus 50 newtons. You're going to end up with minus 33.9 newtons plus Fn equals to 0. So you take this guy to the other side, you're going to end up with Fn equals to 33.9 newtons. So your normal force is going to be 33.9 newtons. Now we know the friction force and we know the normal force. Our friction force is 19.2 newtons. Our normal force is 33.9 newtons. With this information, if you know the friction and the normal force, then you can always find what the coefficient is. The friction force is going to be equals to, since this particular object is moving, so it's going to be kinetic friction you have found. The kinetic friction is going to be equals to the coefficient of kinetic friction multiplied by the normal force. Then you divide both sides by the normal force, you're going to end up with the coefficient of kinetic friction will be equals to the kinetic friction divided by the normal force. The friction you found was 19.2 newtons and the normal force you found was 33.9 newtons. You divide 19.2 newtons by 33.9 newtons, you're going to end up with 0.57 as your coefficient of friction. Now, the one thing I want to emphasize when you're doing this kind of stuff, no one has to tell you to say add the x components, then add the y component. You just need to do it, because that's one of the steps you have to go through. You need to add this plus this plus this plus that. Even if you don't understand what the question is saying, just add these things, then things will start coming out on their own. Add this plus this plus this plus that, then things will start coming out on their own. Are we clear? Is it clear to everyone?
Yes, sir.
Yes, sir.
Now, this question is not complete. But anyway, I'll try to explain what you're supposed to do, because there's some piece of information which we don't have. Okay. Example 3. The object in figure 3 is in equilibrium, so it's not moving. Find the normal force Fn. So in this particular case, figure 3, if you look at figure 3, what you have, this is what you have. Like this. Now, in this particular case, there is something which we don't know, which we need to know. And the thing which we need to know is the angle of the incline. This angle of the incline, we need to know this. So this information here has not been provided. So you can't kind of do anything very much. But there's something you can do, because you can use this knowledge for other things also. So this incline, this angle, theta, needs to be given. Whether it's 30 or 35 or 25 or 20 degrees, we need to be given this angle theta, and we have not been told how much it is. So we can't find the stuff which we really need to find. But this thing is on an incline. Okay? So I'll try to explain this as much as I can. So this thing is an incline. Now, we are told that this box is not moving. Are we clear? This is a motionless box on an incline. So this box is experiencing what is referred to as static equilibrium. You always have to make the distinction with what kind of equilibrium is there. So in this particular case, what we have is something called static equilibrium. Okay, so the question is, who is not supposed to move? You always need to identify which guy is supposed to be in equilibrium. In this particular case, it is the box, which is supposed to be in equilibrium. Okay, fine. We have found out, okay, fine, it's the box which is supposed to be in equilibrium. The other thing which you need to find out after you identify, say, okay, it's the box which is supposed to be in equilibrium. The other thing you're supposed to do next is, we can assume, right on your printed notes, you can just give this angle to be 30 degrees. Let's say theta is equal to 30 degrees. If theta is equal to 30 degrees here, then this angle here also is equal to 30 degrees. So let's just assume that theta is 30 degrees. Are we clear? So On your printed notes, put an angle, say here, theta is going to be equal to 30 degrees. Because this angle needs to be known how much it is for you to make any progress with this problem. Okay? So the next thing you need to do is which forces are acting on this particular box. Well, luckily we have been shown which forces. There is this one here. This one is the weight of the box. This 200 newtons we are seeing here. The 200 newtons we are seeing here is the weight of the box. Are we clear? Okay. Now this 200 Newton is split, can be broken up into an X component, which is what is shown here, and a Y component, which is what is shown here. But we're going to do this breaking up when we are working out what are the components of the weight. What are the components of the weight? So what we are going to do is the following. Okay, what you're going to do is the following. We are going to, for the time being, we're going to ignore, we're just going to leave it the way it is, because the first thing we're supposed to do is just to identify which forces are acting on this particular object. So we have got the weight, which is in this direction. The other kind of force which is acting on this particular object is this object would like to slide down this way. Usually on an incline, things tend to slide this way. But since our object is not sliding, the reason why it's not sliding is because of this friction. This side. So we have identified two forces, obvious forces. There is the weight of the box, and there is also the friction which is pointing in this side. So after you identify the forces acting on your box, the next thing you have to do is you need to draw an XY plane over the object you are looking at. Now, when an object is on an incline, you would draw your X axis so that it's parallel to the incline. So your X axis will be in this direction, parallel to the incline. And your Y axis is going to be perpendicular to the incline. Are we clear? So on top of this line here, you draw using a pencil or your ruler a straight line parallel to the incline going this way. That's going to be your x-axis. So that's going to be your x-axis. Then you draw another line at 90 degrees to this line, which is supposed to pass through this line. That's going to be your y-axis. So you have drawn your x-axis, you have drawn your y-axis. Now, once you draw your x-axis and the y-axis, usually we choose the part of the y-axis above the incline to be positive. So up here will be our positive y-axis, down here will be our negative y-axis. Now, when things are on an incline, the principle is really the same. As much as this object is not moving, if it's allowed to move, it will move downwards this way. If this object had to move, this box had to move, slide, it will not slide up, but it will slide down this way. So in the case where this object has to slide down, we choose the direction in which this particular object is likely to move in to be our positive x-axis. So whether an object is moving or an object is not moving, as long as there is a likelihood that this particular object will move in a particular direction, you choose that direction to be your x-axis. So on an incline, you have your x-axis is drawn parallel to the incline and your y-axis is drawn perpendicular to the incline. So I don't have a pencil. I could have drawn things here. But since you've got a pencil, and that's the reason why I asked people to print out these things so that you can draw and see, so that we can move together through the steps. So you draw your x-axis along this line, you draw your y-axis along this line. Since this box, when it slides, it will come down this way, then the direction in which it's going to slide, that is going to become your positive x-axis. So this side will be your positive x-axis. If this becomes your positive x-axis, then this side will be your negative x-axis. Are we clear?
Yes.
Once you do that, then things become very easy. You start looking for what angle does this friction force make. This friction force, what angle does it make? The friction force makes an angle of how much? 180 degrees. Of course, there's going to be another force which you failed to mention. This one here, the normal force. The normal force, as this particular box is exerting weight on this particular incline, the incline will not be happy. So the incline will be pushing upwards. It will be pushing in this direction. So the normal force will be pointing in this direction, in the direction of the positive y-axis. So there are three forces acting on this box. There is a weight of the box, there is a normal force from the incline, there is also this friction force in that direction. So three forces acting there. So if we have chosen this side of the x-axis to be our positive x-axis, you see that from this side up to where the normal force will be pointing in this particular direction, that's going to be 90 degrees. Then from this side up to where the friction force is pointing, that's going to be 180 degrees. Then from this side, we go around like that all the way up to here. That's going to be 270 degrees. But that's not where the weight is. The weight is here. So it's going to be 270 degrees plus this angle, which we know is the same as the angle of the incline. So the angle which the weight is going to be making is going to be from this side here, which is our positive x-axis. We go around 90, 180, 270, 270 plus 30 degrees. We have said, let's assume that this angle is 30 degrees. So 270 plus 30 degrees is going to give us 300 degrees. So the weight makes an angle of 300 degrees from the positive x-axis. Are we clear? Is it clear?
Yes.
So, the normal force, the angle it makes is 90 degrees. The friction force, the angle it makes is 180 degrees. Then this weight, the angle it makes, if we assume that this theta is 30 degrees, then the angle this weight is going to make with the positive x-axis, which will be this direction, is going to be 300 degrees. So with that information,
No, sir.
Ati? Hello? Are we clear? Is there any question with what you have said, what you have discussed? You are supposed to be drawing the things I'm telling you to do. You are supposed to, by this time, you should have drawn your x-axis like this. You should have drawn your y-axis. This force should be pointing this direction. This normal force should be pointing this direction. The weight is pointing this direction. The friction is pointing this direction. So that you choose this side to be your positive x-axis. This other side will be your negative x-axis. This side here will be your positive y-axis. Down here will be your negative y-axis. So that when you measure your angle from this side up to where this normal force is pointing in this direction, that's 90. From this side up to where this guy is pointing, that's 180 degrees. From this side, you go around like this, because you always measure your angles from the positive x-axis. You go round this way like that. Up to here, you're going to have 270. Then 270 plus what this angle is here. That's a 30 degrees. You're going to have 300 degrees. Are we clear? Hello?
Yes, sir, it's clear.
So once you do that, then you start
Yes,
with
sir.
you start with the weight. So the weight, which is the weight of the box, the weight of the box is going to be 200 degrees cos. Remove this theta, you put 300 there. So 200 degrees cos 300 degrees. I don't know what you're going to get because where's my calculator? Where have I put it? Okay, here it is. So 200 times cos 300 degrees, you're going to have 0 degrees. No, not 0 degrees. Something. I think my son changed the calculator a bit. Just a minute. Okay. So 200 times cos 300 degrees, you're going to have 100. So this bit, 200 cos 300 degrees, should give you 100 here. So you should have 100 here. Then this other side, 200 times sine 300, you should have negative 173.2. So this one should give you negative 173.2. This one here should give you 100. Are we clear? So you do that. You write 200 cos 300, that should give you 100 degrees here. Then 200 sine 300, that should give you minus 173.2 newtons. Then we'll move on to this guy here. This bit here. The normal force. The normal force will be pointing, which is this one. You lift it from here, you put it so that it's pointing up there. You're not changing anything. The direction is still the same. Whatever the size of this normal force is also the same. So you're going to have, for normal force, you're going to have Fn cos 90 degrees, that will give you a 0. Then you're going to have Fn sine 90 degrees, you're going to have Fn. Then when it comes to the friction force is pointing in this direction. The friction force is pointing in this direction. We have chosen this direction to be our positive x-axis, so the angle the friction force makes is going to be 180 degrees. So you're going to have your friction force, the x component of the friction force is going to be Fx cos, change the 0 here so that it becomes 180 degrees. So Ff cos 180 degrees is going to give you minus Ff. Then this side, Ff sine 180 degrees is simply going to give you 0. So here we have this bit here. This is 100 newtons plus 0 newtons plus minus Ff. So when you do that, when you add those things here, when we do the addition, the sum of the forces along the x-axis should be equal to 0. So you're going to have this bit here is going to be 100 plus 0 newtons plus minus Ff equals to 0. So we end up having 100 minus Ff equals to 0. So we end up having Ff being equals to 100 newtons. Are we clear?
Yes, sir.
Then this side, your 200 sine 300 degrees, that's what we found as minus 173.2. So it's going to be minus 173.2 plus normal force plus 0 degrees. So it's going to be minus 173.2 plus that. So you're going to end up having your normal force being equals to, your normal force being equals to normal force being equals to 173. So we have got a friction. The friction force we find to be 100 newtons. Then your normal force by doing this, so we're going to have here, this is going to be minus 173. So you scrap out this thing here, you put minus 173.2 newtons plus the normal force plus 0 degrees plus 0 newtons equals to 0. So there we're going to end up having your normal force being equals to 173. Okay, 173.2. Using this normal force and using the friction force, you can actually find out the coefficient of static friction, because if the friction comes out to be 100 newtons, then the normal force is 173.2 newtons. You can use this expression which you have up in the other problem. You can use this expression, this, to find out what is the coefficient of friction. So in that particular case, you're going to have 100 newtons divided by 173.2 and your coefficient of friction is going to be 5.75 again, like we have here. Are we clear?
Yes, sir.
There are some steps which you have to follow. The first step is you need to identify which object needs to be in equilibrium. When we're talking about equilibrium, we simply mean that this particular object, either it remains motionless or this particular object can move. But if it's moving, it needs to move at constant speed. So you identify the object which needs to be in equilibrium. Then once you identify the object which needs to be equilibrium, the next step is to identify which forces are acting on this particular object. You identify, there's definitely, if it's an object, there's definitely weight. The normal force. There might be some friction force, or there might be some force pulling the object through a rope. All these forces have to be identified. Once you identify these forces, then you draw an XY plane most likely at the center of this particular object. Once you draw an XY plane at the center of this particular object, if this object is not going to move in any way, you can choose which one is going to be your x-axis. You choose which one is going to be your positive x-axis, negative x-axis, and above the object, that's most definitely going to be the positive y-axis. Below the object, that's definitely going to be the negative y-axis. Then the forces you have, you can move them so that they start from the origin of your x-axis, your xy plane. Once you place your forces nicely, by making sure you don't change the direction and the size of the forces remains the same, once you do that, then you can now work out the components of the forces by putting them in that table of components. For each force, you work out the x component, the y component, x component and y components, x components and y components. Then after that, after you do that, the next thing you do is you add up the components. When you add up the x components, they should give you 0. When you add up the y components, they should give you 0. When you force them to do that, then it will be possible for you to do whatever it is you want to do. Okay. Any questions? So we stop here. Now, we stop here. Unless there are any questions. Do you have any questions? Okay, so if there are no questions, we'll see you next week.
All right, sir.
Have a good weekend.